Hello friends, welcome to our today class and today class is trees। ग्राफ थ्योरी के अंदर ये एक टॉपिक आता है ट्री का, वो आज हम डिस्कस करेंगे। ट्री इज ए डिस्क्रीट स्ट्रक्चर दैट रिप्रेजेंट्स हायरार्किकल relationships between individual elements or nodes। A tree in which a parent has no more than two children is called a tree and its properties. Definition: a tree is a connected acyclic undirected graph. There is a unique path between every pair of vertices in G. A tree with n number of vertices contains n-1 number of edges. The vertex which is of 0 degree is called root of the tree. The vertex which is of 1 degree is called leaf node of the tree, and the degree of an internal node is at least 2. For example, see this. Next is centers and bicenters of a tree. You will clearly understand by this. The center of a tree is a vertex with minimal eccentricity. The eccentricity of a vertex x in a tree G is the maximum distance between the vertex x and any other vertex of the tree. The maximum eccentricity is the tree diameter. If a tree has only one center, it is called central tree, and if a tree has only more than one center, then it is called bicentral tree. Every tree is either central or bicentral. Algorithm to find central and bicentral of a tree. Step first, remove all the vertex of degree 1 from the given tree and also remove their incident edges. Step number 2, repeat step first. Either a single vertex or two vertices joined by an edge is left. If a single vertex is left, then it is the center of the tree, and if two vertices joined by an edge is left, then it is the bicenter of the tree. Now this will be easily understood by this problem. The problem number first, find out the center oblique bicenter of the following tree. अब आप इस ट्री को ध्यान से देखिए. Okay, now solution. At first we will remove all vertex of degree 1 and also remove their incident edges and get the following tree. Here, if you will remove all the edges, then you will find this. Okay, again we will remove all vertices of degree 1 and also remove their incident edges and get the following. Okay, this and this will be removed, then you will get only C. Finally, we get a single vertex C and we stop the algorithm. As there is single vertex, this tree has one center C and the tree is a central tree. Understand it? You can also see the problem of type 2 here. Next is labeled tree. A labeled tree is a tree the vertex of which are assigned unique numbers from 1 to n. We can count such trees for small values of n by hand so as to conjective a general formula. The number of labeled trees of n number of vertices is n minus 2. Two labeled trees are isomorphic if their graphs are isomorphic and the corresponding point of two trees have the same label. This is the example. You can easily see and easily understand it. Next is unlabeled tree. An unlabeled tree is a tree the vertex of which are not assigned any numbers. The number of labeled trees of n number of vertex is 2n, n plus 1 and this type of. This is the example. Next is rooted tree. A rooted tree Z is a connected acyclic graph with a special node that is called the root of the tree, and every edge directly or indirectly originates from the root. An ordered rooted tree is a rooted tree where the children of each internal vertex are ordered. If every internal vertex of a rooted tree has not more than m children, it is called an m-array tree. If internal vertex of a rooted tree has exactly m children, it is called a full m-array tree. If m is equal to 2, the rooted tree is called a binary tree. See here, these are the root nodes, these are the internal nodes, and last are the leaf nodes. Okay, next coming is binary search tree. Binary search tree is a binary tree which satisfies the following properties. X in left subtree of vertex V value is X is less than value V, and Y in the right subtree of vertex V value Y is greater than value V. So the value of all the vertices of the left subtree of an internal node V are less than or equal to V, and the value of all the vertices of the right subtree of the internal node V are greater than or equal to V. The number of links from the root node to the deepest node is the highest of the binary search tree. This is the example. You can note this graph in your paper, and then you can follow the below steps one by one so that you can easily understand it. Okay, this is the algorithm to search for a key in the binary search tree. Here BST stand for binary search tree. Complexity of binary search tree in this way. And our next topic is spanning tree. A spanning tree of a connected and directed graph G is a tree that minimally includes all the vertex of G. A graph may have many spanning trees, like as in this way. And in this a minimum spanning tree, a spanning tree with assigned weight less than or equal to the weight of every possible spanning tree of a weighted, connected, and undirected graph G. It is called minimum spanning tree MST. The weight of a spanning tree is the sum of all the weights assigned to each edge of spanning tree. See here. Next is Kruskal algorithm. Kruskal algorithm is a greedy algorithm that finds a minimum spanning tree for a connected weighted graph. It finds a tree of that graph which includes every vertex and the total weight of all the edges in the graph in the tree is less than or equal to every possible spanning tree. This is the algorithm. You can easily understand by following steps. Step number first. Arrange all the edges of the given graph G, V, E in non-decreasing order as per their edge weight. Step number 2. Choose the smallest weighted edge from the graph and check if it forms a cycle with the spanning tree formed so far. Step number 3. If there is no cycle, includes this edge to the spanning tree, else discard it. Step 4. Repeat step 2 and 3 until v minus 1 number of edges are left in the spanning tree. Now you can understand by this simple problem. Suppose we want to find spanning tree for the following graph G with Kruskal algorithm. This is the tree. Solution is in this way. Please write down on your rough paper so that you can easily understand. And now we will rearrange the table in the ascending order with respect to edge weight. ये देखिए आप यहाँ पे जैसा दिया गया वैसा तो हमने लिख लिया यहाँ पे एज नंबर वर्टेक्स पेयर एज वेट एंड नाउ वी विल इस टेबल के फॉर्मेट में इंक्रीजिंग ऑर्डर में पुट अप करेंगे। तो देखिए जो वेट है वो 29 13 1 तो 1 है वो फर्स्ट आ जाएगा। सी हियर E4 BC vertex and weight is 1 1 2 3 these are the weights in the ascending order. ओके देखिए and next is Prim's algorithm. Prim's algorithm, discovered in 1930 by mathematician Wojtek Zernik and Robert C. Prim, is a greedy algorithm that finds a minimum spanning tree for a connected weighted graph. It finds a tree of that graph which includes every vertex, and the total weight of all the edges in tree is less than or equal to every possible spanning tree. Prim's algorithm is the faster on dense graph algorithm. Initialize the minimal spanning tree with single vertex randomly chosen from the graph. Repeat step 3 and 4 until all the vertices are included in the tree. Select an edge that connects the graph with a vertex not yet in the tree, so that the weight of the edge is minimal and inclusion of the edge does not have a cycle. Add the selected edge and the vertex that it connects to the tree. This is the problem. Suppose we want to find minimum spanning tree for the following graph G using Prim's algorithm. This is the graph. The solution is, here we start with the vertex A and proceed. A से हम स्टार्ट करेंगे. ओके, अब इसमें देखिए आप आगे इस जैसा इसमें दिखाया गया है. इसमें कोई वर्टेक्स ऐड नहीं किया गया है. इसमें आफ्टर एडिंग वर्टेक्स ए हम स्टार्ट हुए, ए से सी पे गए, सी से बी में गए, आफ्टर एडिंग वर्टेक्स सी, आफ्टर एडिंग वर्टेक्स बी एंड सो. ये देखिए, ठीक है. दिस इज द मिनिमल स्पेनिंग ट्री एंड इट्स टोटल वेट इज in this way. So this was our today class. So friends, if you like our today class, then like this video, share with your friends, and if you are new on our YouTube channel, please subscribe our channel and press the bell icon button so that you will get the all our video notification first time. Thank you very much.